Hello, in this video I'm going to give an overview of the forms of aberration that can occur in mirrors and lenses. So this is sources of distortion to our image. We're not getting light reaching a single focal point. So we might get blurring, we might get distortion. And this can creep into mirrors and lenses in different ways. I mean, the three most common ways are we've got spherical aberration. So this is where we've got light either refracting or reflecting from a spherical surface. So we've said a few times before that it's parabolic surfaces that are the surfaces that we really want, but they're more difficult and more expensive to manufacture. So we often get a lot of spherical surfaces, particularly in lenses, and these don't refract or reflect in as well as good a fashion as a parabolic surface. So say we've got a plano convex lens such as this. Our first surface here, say it was spherical, so better than the drawing I've actually done. We've got this spherical surface, we've got this parallel light coming in. The stuff hitting in the middle is just going straight on, but as the rest of the light focuses, depending on how far away we are from this central axis, it's going to have a different focal length. It's going to refract by different amounts and give us different focal points. So at the outside, we might focus in at this point here, but as we're closer to this central axis, we might be focusing, I've kind of exaggerated the effect here, at some point over here. So we've got this range of focal length because of this spherical surface. That's giving us some kind of blurring going on here. We're not getting all of our light focused as we would like. So we want some way of correcting this, really. Sometimes you can live with that. You're not really that fussed, but it's nice if we can correct these things. You're going to get this is where these positive meniscus lenses that I spoke about in the introduction to lenses can be useful. You might put a second lens behind this, so we've got our initial lens like that. You might then do a positive meniscus immediately behind it. So it's got these, remember this is the one where it's thicker in the center than it is at the edge, the positive meniscus. So we've got these two curved surfaces. That can be a good way of correcting for spherical aberration. Of course, that can then create its own problems as well. The more surfaces that you get, the more reflection you're going to get. You can then start getting cascading of reflections going around between all of these different surfaces. You can start getting ghost images. That's the worry of bringing in too many boundaries and too many surfaces into all of these compound lenses. So, I mean, you can minimize that by having certain coatings on the lenses and combining them in certain ways. But then that starts getting more and more expensive. So you've always got trade-offs going on between these things. How much does this spherical aberration actually matter? How much is it affecting your image? And then how much are you going to be introducing new problems by having more surfaces? But still, you can correct it in certain ways. You've got similar trade-offs going on when it comes to chromatic aberration. So this is where you've got different frequencies of light being refracted at different amounts. Blue light bends more than red. So you're going to end up having a similar problem. If we've got our, say we had a biconvex lens, then the blue light is going to end up refracting more than the red light. Again, we've got this dispersion or dispersal. They were the two words I was aiming for. You've got this dispersal again going across by frequency as a function of frequency, where we got different focal lengths for the lens. So again, we want to pull that back. We want to get rid of this chromatic aberration. You quite often get this with doublet lenses. You see this a lot in telescope eyepieces, where you'll combine this biconvex lens with a plano concave lens. But again, you've got, how are we actually combining these? Are you actually sticking these in place in some fashion, so you're eliminating the boundary as much as possible between these? Although quite often these are going to be in different types of glass. So you might have different refractive indices going on here, because otherwise you're just coming back to, you know, what is the advantage of having that over just having a plano convex lens. So you'll have different refractive indices for these two things. You've got to stick them together in some way. How secure is your boundary going to be? You know, how well manufactured are they so these surfaces fit perfectly together? You know, you're going to start getting more reflections. You're going to have to put coatings on the boundary. You're going to be getting ghost images. So this might then correct for your chromatic aberration. That's great. The blue is refracting more here and then refracting back out again. You can start bringing these back to a point, but you might be introducing new problems. So again, trade-offs, much as we've got with a spherical aberration when you're putting these eyepieces together. And this is where you can start getting very expensive eyepieces, you know, hundreds or thousands of pounds you'll be spending on an eyepiece if you're getting really, really concerned about the aberrations brought in due to spherical or chromatic effects. Right, the last one I'm going to mention is coma. And this is an unavoidable result, even with a parabolic mirror. So say you've got a parabolic mirror, it's set up for parallel light coming in. That's great. You know, so we've got our Newtonian reflector. You're thinking, great, we've got parallel light coming in, and that's going to then focus down perfectly to our secondary mirror and then go off to our eyepiece. Wonderful. You know, parallel light, parabolic mirror, brilliant focusing. But what if you've got stuff which is not at the center of your field of view? You're not pointing the telescope directly at it. You've got something which is slightly off axis. It's not pointed directly at this object. We've got light coming in that isn't well, is parallel, but not parallel to the axis of the telescope. It's not parallel and coming in perfectly for focusing off of this parabolic mirror. Then you're getting this light that's coming in and it's not focused perfectly on the secondary mirror. You get this distortion effect. It's a bit like looking at a comet, that if you've got your field of view on a telescope, everything can look great in the middle. And then you get over to the edge. If you've got some bright object on the edge, rather than having a nice point, you can get these little blurring effects that look like little tails going on. And if you're looking at something which is more of an extended object, like if you had a planet over the edge here, you've actually got a disk. Rather than having a circular disk, you'll end up getting a sort of wonky sort of disk. It will go off in these comet-like tails off to the side, and that's what's referred to as coma, this distortion towards the edge of the field of view, because it's these objects that are on the edge of the field of view that aren't giving us the perfect parallel light that the parabolic mirror is focusing. So again, you need some kind of, if you're bothered by that, quite often you're not bothered by that, you're just looking at the stuff in the middle of the field of view, but sometimes you are bothered by that, and you again want a corrective lens. So you can get these things called coma correctors. These quite often use negative meniscuses. So here we've used a positive meniscus to correct for spherical aberration, where you might have a negative meniscus. So these are the ones which are thinner in the middle than at the edge. So we've got the two curved surfaces, but it's a narrower gap in the middle than it is at the edge of the lens. These can be good for correcting for coma, and other sort of diverging lenses as well can also be used in coma correctors. I mean, usually if you're an amateur astronomer, typical backguard astronomer, coma isn't a massive problem really. I mean, sometimes you get telescopes where some of the coma correction can get built into it. Sometimes you'll get telescopes which have got an oversized mirror to try and, you know, mitigate things a little bit. So there are various things. I mean, personally, I dabble in astronomy. I've never been that bothered by coma particularly. It's just not something, particularly if you're in an urban area, you'll be looking at something. Say you're looking at a planet, you're looking at Jupiter or Saturn in your field of view. There's only so much magnification you're going to want to try and put onto the planet. I mean, there's only so much light you've got available. You might have a field of view with Jupiter sitting in the middle of like that, nothing else going on. You don't care about coma around the edge. You might have Saturn sitting in field of view. Again, so what? Doesn't really matter. But if you're a more enthusiastic and advanced amateur astronomer, then it's going to bother you a little bit more. So there's 3 types of aberration that can creep in to, or will creep in to your observing: spherical, chromatic, and then coma. So it's just useful to know where these things come from and the different ways that they can get corrected for. And you'll see this in descriptions of certain eyepieces. They'll say, oh yeah, if you use a particular eyepiece, it's great for correcting your chromatic aberration and things like that. So yeah, useful if you start getting into buying a lot of equipment and you want to know what you're getting your money for, if you're going to be paying out loads of cash in order to get a better eyepiece for your chromatic aberration. So there you go, quick summary of all of that.